Hello everyone and welcome back. My name is Mr. Koval, and in this video I'm going to be talking about the solubility product constant, or KSP, and molar solubility. So let's talk about what solubility is. So solubility, first and foremost, is basically the quantity of a product that dissolves in a certain amount of liquid. And a lot of times when you look up solubility, you'll find that, it's the number of grams of your product per 100 grams of water, right? So that's a lot of times when you see a solubility curve or something like that, you'll see the solubility written in terms of grams of compound per 100 grams of your water. But here with molar solubility, so right here, molar solubility, which is S, it's usually a capital italicized S. Sorry, it doesn't look italicized. Um, so, what is molar solubility? As the name suggests, it's solubility, but we're using moles, and we're going to be using liters. So, solubility is going to be in units of moles per liter of your solution. So it kind of reminds you of the concentration or molarity. So moles per liter, how many moles are dissolved in a given liter of substance? So if we use an example, let's use silver chloride as an example. So here I've written the equilibrium expression, or not the expression, but the equilibrium equation for the silver chloride. So here, silver chloride is a solid, and it's going to dissolve into its two ions, your silver ion and your chloride ion. And these are aqueous because they're dissolved in water. And so these can come back and reform some solid. And so here we have the KSP, which is your solubility product constant. That's what the SP, solubility product. K is your constant. This is not the solubility, right? So this is not the solubility. Don't confuse this with solubility. This is just the solubility product constant, okay? And it's an equilibrium constant. So this tells you how far to the left or right your equation is, and you can see that this is very small, right? So that means that the reactant, or in this case, the solid, is favored. So you could see that this is not going to dissolve very much. So let's talk about KSP and solubility a little bit more. So KSP has only one value at a given temperature, right? So change temperature, you change the KSP, just like any equilibrium constant. So there's only one value for your KSP. So the KSP for this dissolving, this equilibrium here, is going to be 1.77 times 10 to the negative 10 at that particular temperature. So if we're assuming room temperature or 25 degrees, then that KSP is going to be the KSP at 25 degrees. Change the temperature, and it's going to be a different value. Okay, but at any given temperature, solubility can be solubility itself, not KSP, but solubility can be different, have different values in different kinds of solutions. So, for example, what if I have a solution of what if I have silver chloride mixed in pure water versus that of, say, a sodium chloride solution, right? Where I will find that the solubility of silver chloride is going to be different in pure water than it is in a sodium chloride solution because of the common ion effect. Because I already have chloride ions here in solution, that's going to cause the silver chloride not to be as soluble because of Le Chatelier's principle, right? So you have more chloride ions. That's going to shift this more towards this way. So it's going to be less soluble. So the solubility is going to be different. Also, the solubility of silver chloride is going to be directly related to the amount of chloride ions and silver ions that are in solution at equilibrium. So what does that mean? That means that solving or finding the molar solubility, finding how much dissolves in your solution, from the KSP is going to involve solving an equilibrium problem, which means an ice table. So let's go ahead and do an example. Let's use this and do an ice table to see what the molar solubility of silver chloride is. So hold on just a moment. Okay, welcome back. So here I have my equilibrium table. So my ice table is here. And so we're going to use this example where the silver chloride is dissolving in pure water. So the KSP is 1.77 times 10 to the negative 10. And so using our ice table, we can say, okay, so initially, when we throw our solid into the pure water, we're going to have zero of our ions, zero concentration. So here I have my silver ion concentration, my chloride ion concentration. Notice I don't have this in my table because it's a solid and it's not involved. Because remember, solids and liquids, their concentrations don't change. Their concentrations are constant. So we only want the concentrations that change here. So we have initially zero moles per liter for these two, for our ions, because nothing is dissolved at the beginning. So what's the change? So normally we would use X as our change, right? So we notice here that for every 1 mole of your silver chloride that dissolves, you get 1 mole of your silver ion and 1 mole of your chloride ion. And so we can represent that if you wanted with X like we normally do. So this would be a plus X or plus X. But since molar solubility is going to be defined as moles per liter, which is the concentration of molarity, so then we can use just a symbol, we can use our molar solubility. So molar solubility would be X in this case, or you could use a symbol S. So we could use S as the change. So we know that when we start with this, we're going to get a certain amount dissolved. So that's going to be S here and S here. So plus S plus S. And knowing me and keeping in mind that here the change is the amount that's dissolved, right? So which is the molar solubility. So we could use S as our value here, or S as our variable. So then when we add these together, of course, you get S here at equilibrium, and you get S here at equilibrium. And so now we can set this equal to our equilibrium expression. So remember, so in this case, since we have just these and there's no coefficients, or the coefficient is 1, then the KSP expression is going to be equal to the concentrations of these two. So the concentration of Ag plus multiplied by the concentration of Cl minus. And again, the coefficients are 1, so the powers are 1. And so now we just plug in these values, right? So S and S gets plugged into here. So KSP is equal to S times S, which is S squared. And then this KSP is equal to this. So that means that S squared is equal to 1.77 times 10 to the negative 10. Take the square root of both of these, and you get S is equal to 1.33 times 10 to the negative 5 molar. And so that is the molar solubility of silver chloride in pure water, given that that is the KSP value. And so that's how you would solve for your molar solubility if you're given the KSP of your substance, and you know what the salt is, and you can write out the equilibrium equation for dissolving of that ionic substance. So I hope this video was helpful. If you enjoyed this video, if you like this video, then please hit that like button right there, and also subscribe to my channel. Hit that notification bell so you can be notified by other videos I put out, and put a comment down below in the comment section. Let me know what you think. Ask me questions. I'd love to hear from you. Thanks for joining me. Have a great day.